As with all sessions, feedback is very much appreciated. All the speakers here are trying to improve our presentation, so I'd love to hear your feedback. If you think it's great, that's awesome. If you don't like this, that's awesome too. Just please, type some words and explain to me why, and that would be very helpful for the future. I'd appreciate it. Our agenda today is pretty brief since this is a short session, but essentially we're going to be talking about both relational and non-relational databases and how they differ, and the pros and cons and use cases of each. So just to start off with a flat-out easy comparison here of relational versus non-relational, right? We have some very differing things and different properties, right? So relational databases are, of course, based on the relational model. Your data is going to be stored in, tables, which I'm guessing many of us are familiar with, and the schema and any constraints on that data are going to be strictly enforced by the database. So it's going to make sure that everything is in line with where it should be at all times. When you're working with relational databases, having data that is normalized tends to work best. This is where you place the data in certain forms, known as normal forms, that can help enhance the performance of the database and make querying easier and make lots of good things possible. When data tends to violate those relational rules or normal forms, that's when you usually can end up with bad things happening. So we'll take a look at that. On the other side of the spectrum, we have the non-relational or NoSQL databases, and I'm going to use those terms interchangeably today. This is based on other models, so not the relational model. And there are several models actually for non-relational databases. There's key value databases, there's graph, there's document databases, there's column store type databases. So there's multiple models that can fit under that umbrella. The data is, of course, then not stored in table structures. It's stored in something different depending on what model is being used. And also in a NoSQL database, the constraints, instead of being enforced by the database, they're typically enforced by the application instead. Now, some databases do allow some level of constraint support and enforcement at the database level, but usually this is taking place in the application instead. There's also tends to be no rigid schema that's really present, which can have advantages and disadvantages, as we'll see. And at least originally, NoSQL databases were considered really good to be used with scale-out deployments. This is because of the types of consistency they allow. It makes it usually very easy to spread out over a wide area, and this is one of the initial things that really got them to catch on. So to talk about normal forms very briefly, just to explain what they mean and what can happen when you're violating them, let's take a look at the first normal form, the most simple normal form of a relational database. And that normal form states that every table cell should contain a single value. So pretend with me now if we had a table that contained two columns, an ID and some names. In this particular, as it's shown on the screen here, well, that first row, that first record, has 3 different names in it. Right? It would be very difficult to select the record where the name is Kathy. We'd have to use some kind of a text function to figure out if it was present, and then we'd still have this entire row selected with all the other names that we maybe didn't want. Right? This is violating the first normal form. If we were to restructure the data instead to put it in line with the first normal form, we'd have to give each value its own record, right? And we can relate them together by giving it all the same class ID. So that's how we put something in compliance with the first normal form. That's pretty simple. The second one builds on that a little bit. So the second normal form says any non-key attribute is dependent on the primary key. So as another example here, let's take a little bit larger table now. We have 3 columns. We have auto manufacturer, model of a vehicle they make, and the country they are headquartered in. Right? So we have Audi with the Q5 and the R8 there in Germany, and then we got Tesla and Land Rover as well. Problem here is that the country attribute is dependent on the primary key, but it's duplicated at this point, right? The country, Germany, that Audi is headquartered in, that's dependent on Audi, not the model. That's not going to change. So what we could do instead is put this in line with the second normal form and actually split it up into 2 tables, right? We'd have a table with the auto manufacturer's name, the make, and the country, and then another one with the make and the model. And we'd have to join those together in a query if we wanted to see the results as we had them before, but this would store it in a form that is aligned with the second normal form. Lastly, we'll look at the third normal form here. This builds on the second normal form and says every column is directly related to the primary key, but not to any other column. So if we have another table here, this time we have Academy Award winners for select movies. We have 4 records here, so we have Best Actress won twice by Vivian Leigh, 1939 for Gone with the Wind and 1951 for Streetcar Named Desire, I believe, and then Bing Crosby and Yul Brynner as well. And we're storing the award they won, the year they won it, their name, and their date of birth. Now, once again, the date of birth isn't really dependent on the actual winning of the award. It's dependent on the person. So again, we want to split this up into two different tables to bring it into alignment with the third normal form. We'd have a table with the winner's name and their date of birth, because those two are directly related, and then the actual award, year, and the winner, because that's all related. And again, we join that together if we needed to. There are other normal forms as well. There's Boyce-Codd normal form, fourth and fifth normal form. If you're getting into a place where you need to care about these, you're probably working in some kind of academia. This is usually where the optimization gets so detailed that it becomes impractical and becomes a barrier to getting work done. I was working once on a database that was storing octets, so IP addresses, and it had every octet split out separately. So you'd actually have to reassemble the IP address in a query to return it as something that would be useful. Extremely normalized, didn't really provide any value at that point either. So in order to get a database that is, of course, in accordance with these normal forms we just talked about, there's a whole bunch of design and thought that usually goes into place ahead of time. And if we go look at a NoSQL database, in this case a document database from Azure Cosmos DB, this is a record, right? This is a document, it's a JSON document. A little different here because everything's dynamic. We can add new properties on the fly for individual records. We don't have to go through the trouble of, I need to alter my database and alter the table and add a column and decide a data type. We can just add stuff, right? And it will accommodate that and index this. This particular record is for a system I use that actually does URL redirects. So if you were to go to sqlbob.com/zombocom, it would then read this record and redirect you to zombo.com. And if you're busy sometime, you should go there and check it out. It's an experience. But the point is we have rather simple design in this case of a document, and this is handling everything. Now, they could have easily implemented this as well with a single table in a relational database, but I decided to go with this just to kind of demonstrate how simple it can be to create an object in a non-relational database. Now, a lot of people will say that because it's NoSQL, well, there's not really a schema, and there's not really any design, but this isn't actually true, right? NoSQL schemas do exist. And as I mentioned before, they can be somewhat supported by the database, somewhat enforced by the database, but they're usually fully enforced by the application instead. This can make things a lot easier, especially if you're making a deployment, right? If all I have to deploy is a change to my application and the database will be able to handle it, makes things a lot simpler than having to make sure the database has the columns I need to populate first, and then I can roll out the application change, or maybe the application change has to have a switch or some kind of logical check to make sure the fields it's looking for exist before it goes on and actually makes use of them. There's still lots of design decisions that need to happen early on with a non-relational database, and if you're wrong, you can definitely have to pay for them later. A lot of times this is particularly related to choices of what fields the data might be partitioned on or what field is a key. These are things you really got to think about ahead of time, because if you make a poor choice, you might have to redesign your entire non-relational database to fix the issue. So to talk briefly about how partitioning works and why this is important, I'm going to use Azure Cosmos DB as an example. So I have a Cosmos DB container. It's a document container, so we're using documents again, kind of like I showed you before, for a sample messaging application. Well, let's say we have our messaging application, and our partitioning key in this case is going to be the user ID. Okay, and the users of this application, well, we'll see in a second here. So the way this works is Cosmos DB will take the partition key, in this case the user ID, and hash it, and this will create a somewhat randomized distribution of hash values across all the different values of the user ID, which is really good. And then it will divide them up into physical partitions, right? So if we had a messaging application here, making use of the characters from the wonderful TV show Paw Patrol, if any of you are familiar with that, if you have young children in your life at some point, you might have seen this. I'm sorry if you did, but Cosmos DB will divide this up into physical partitions and then logical partitions. So a logical partition is just a different value of the key, but that logical partition may share a physical partition with one or more other values depending. So in this case, it is based on the amount of data that each key value has. For some reason, Chase, the police dog, tends to be the most popular member of the Paw Patrol, so he might need an entire partition for his own, while some of the lesser characters like Captain Turbot and Robot Dog probably would have less, and they could end up sharing a partition. One of the few hard limits in Cosmos DB is that a physical partition can only contain 20 gigabytes worth of data. You can have an infinite number of physical partitions, but you're limited to 20 gigabytes per partition. So you can end up in a case where maybe you have so much data that you need to add a new partition on, right? This could be an issue, or you would think it would be an issue. What happens if we need to grow and add something else? Well, this is where a lot of non-relational databases, and especially Cosmos DB, really shine because it can just dynamically add partitions in the background without affecting anything, right? It can actually split the partition up kind of like, in some ways, similar to a page split in SQL Server. If you're familiar with that, it will add the new value and create a new physical partition. You'll be good to go. Now, as again I mentioned, there is a 20 gigabyte limit, and probably one of the biggest things to think of with that is make sure you don't end up with more than 20 gigabytes of data per partition. So partitioning on just a username in this case might not be good enough. We might have to throw something like a date in there as well to really make sure we have lots of different values. But that's okay because this is a logical construct. For greatest efficiency, queries always want to eliminate partitions in a situation like this. Kind of similar to how in SQL Server, if you're using partitioning, same idea. If I have multiple partitions and my query specifies the field, which is the partition key, then the database knows, well, I only need to search a partition to find what I'm looking for. If it doesn't know which partition to search, then it has to fan out and search everything, and that can affect performance. And in case of cloud services like Cosmos DB, you can end up paying more as well because you're creating more I/O operations. So if you have a situation where you can eliminate fan out by querying with the partition key, that can really help you. And again, this goes back to planning. What is your partition key? Know your workload, know your data, and how it's going to be used. Pardon me. So yes, choose a good partition key, understand your workload, know what your most frequent and most expensive queries are, understand the ratios of inserting versus updating, and remember, as I said, these partition keys are logical, so you can't really have too many. Don't be afraid of having too many, because the more values you have, the better scalability you can create. Now, going back to database rules for a minute, in relational databases, of course, we have ACID. I'm sure most of us are familiar with this, right? Relational databases guarantee that everything will be atomic, it will be consistent, it will be isolated and durable. This is really good. We want to make sure our database is always in a consistent state and that it's able to roll back if necessary. And it's durable, everything's persisted once it gets committed. On the other side of the spectrum, in the NoSQL land, they were clever and they came up with base. So general rules of a non-relational database are it's basically available. So we're going to make sure the data is available, usually by replicating over multiple nodes to make sure it's safe in that form. There's a sense of a softer state. So instead of the database enforcing the consistency, like I said, this is where usually developers in the application will handle that part for you. And the E, the last one, the one that used to be the butt of so many jokes, eventually consistent, right? If consistency is not there, reads are still possible. The database isn't going to make you stop and wait because it's waiting for something to update. It's just going to provide you with an older data point in the meantime. So you need to make sure that's okay. Now, a lot of non-relational databases are distributed databases, so we have some other things to think about. One of them is known as Brewer's cap theorem of distributed databases, and this is where you can have consistency, availability, or partition tolerance. You need to pick two. Right, so if you're looking for something like the most recent write, you want to make sure you have that consistency and you want to have that availability, well, then you're probably not going to have partition tolerance. Now, one of the issues with this, talking about consistency, because that's a major difference between relational and non-relational systems, is that there is no consistent definition of the word consistent in computer science. Right, when we're talking about consistency in terms of ACID, we're talking about transaction moving from one valid state to another valid state or being able to roll back. Meanwhile, if we're talking about Replication, for in terms of a NoSQL database, we're looking to get a consistent view across replicated copies of that data. And that doesn't even cover all the cases. There's actually a better kind of umbrella theorem for that, known as the Pekelk theorem, right? And this is saying you can have partitioning with availability versus consistency, or you can just have latency versus consistency if partitioning is not available. So you need to make this choice. To kind of put this in something that might be a little easier to digest, consider a giant distributed database where a reader is really far away from a writer. Maybe they're in different countries on opposite sides of the planet, something like that. If the writer updates the value, what should the reader do? Should the reader just return the old value because the new value isn't there yet? Should it show the same result as what the master copy has, or should it wait for that new value and prioritize that consistency, but you're going to pay for it in terms of performance? There's a lot of ways you can handle this. Going back to my example of Azure Cosmos DB, it actually gives you 5 different consistency models you can pick from. So you can choose what's getting prioritized. Do I really want that strong consistency? Do I not care? And I'll deal with eventual consistency. Or there's some extra settings in between depending on what your application and what your business requirements are. So combining all that, which database should I really use when? Really bad idea for a relational database, any kind of logging. Logs are terrible, right? They're mostly written. They're not usually read unless you're diagnosing a problem. They're usually written synchronously, right? You want that application to log something right away. So if something breaks, you have record of that in the log. And they're usually, not random. They're sequential, tend to be kept for a period of time and then disposed of if there's not an issue. Logs are not normalized and they're not first normal form compliant, right? We have lots of different data that can be in a line of a log. If we needed to search for that, we might have to use a wildcard of some sort or text function that'll probably slow us down more. Logs are not transactional. And most importantly, if the database fails, then we can't log anything, right? This is why SQL Server doesn't even log to itself. It logs to text files. In short, don't try to use the database for something that a file system can do. In this particular case, you could write it out to a text file and be just as good. Database doesn't really add anything to that. Another bad idea, right? Images. They're horrible, right? These are binary large objects. They tend to be big. They're usually written once, and then you have to read them in their entirety if you want to do anything with them. There's no cherry picking which part of an image binary you're going to read. Not only will it grow your database and make your database larger, backups larger, they don't usually compress. Again, they're not transactional, and the database isn't adding any value to them. So again, this is use the file system instead. How about lots of text? I used to work in healthcare. We had lots of medical notes, lots of big text documents. Relational databases don't add much to this either, right? You'd end up using a lot of wildcards to try to search for anything, or maybe use a text search engine to index it all, which it takes it out of the database for that part entirely. This is where something like a document-based database might really help. Generally, bad ideas for NoSQL is anything where strict ACID is required. If you have financial information, or if you're requiring transactional capabilities, this is where I wouldn't bother with a NoSQL database in that case. Another thing is if the database is already relational, or if the data is already relational or can be easily made relational, I wouldn't just put it in a NoSQL database just because. If the data is already in one model, don't change it just for that sake. And then finally, great ideas for NoSQL. Well, anything that's schemaless or unstructured or denormalized. If you have massive scale out requirements, or if you have data that would best be represented in a single table in a relational database where no joining is necessary, this is where I'd start to consider putting it in a non-relational database. And that is everything I have right on the dot. So I would appreciate your feedback. If you have any questions, please let me know.